In this chapter, we're going to talk a little bit about random networks and how they compare to real-world networks. Now, the fact of the matter is that we've already talked about that real-world networks don't behave the same way that random networks do. And so the question is kind of, well, why would we want to even bother talking about random networks then? And I think that question can be answered basically by saying that we want a standard by which we can judge the behavior of real-world networks, and that standard's going to be random networks. And so this week, in both the conceptual part and the applied part, you're going to explore some of the differences between them. Barabashi presents an example of how a random network might behave in the start of the textbook chapter. Suppose you're at a party and there's people mingling. People are in random groups and are randomly going from group to group. There happen to be 2 bottles of wine, and one of them is very cheap and doesn't taste very good, and the other one's very expensive and is very palatable. As the host, you tell someone who's in one of these networks about the expensive wine. And of course, because they want to seem like a connoisseur, or maybe they are a connoisseur, as they start to connect with other people at the party, they start sharing this information. This happens in a somewhat random fashion until everybody at the party is drinking the expensive wine, and you find that the bottle is empty and you have to go out and get more. What we can get from this example is how random networks behave when they're making connections. The behavior that you'll see is as random networks pick up links, you start by having a lot of different disconnected subcomponents until there's a point at which all of the nodes finally become connected. So in this case, that would be the representation that the information about the expensive bottle of wine has been shared with the entire party. This phenomenon at which a critical point is reached, where you suddenly have a giant component, happens quite suddenly. And it actually resembles a phase transition in physics. And as far as we're concerned, it helps explain how random networks evolve. Real-world networks evolve in a little bit different way, and we'll talk about that as we go through the course. So what are the origins of the random network model? You've already been introduced to Paul Erdős and Alfred Renyi. In the middle of the 20th century, they started playing around with random networks. And the way that they talk about random networks forming is they consider every pair of possible nodes in a graph that's totally disconnected. And each time they consider that pair, and they have a value p that represents the probability that the nodes will become connected. So here's the formal definition that a random graph is a graph of n nodes where each pair is connected by probability p. And so you have these random links that get placed all over the graph. Consider a pair of nodes and then check out p and figure out if there's going to be a connection or not based on that probability. And so you can see the result of having a particular number of nodes. Like here we have different graphs of 12 nodes, but you see they have different numbers of links. And that's just kind of how the probability works out. You might have different numbers of links based on what happens when you roll the dice. Here we have graphs of 100 nodes and probability of, 3% that a pair will be connected. And so you can see that they're kind of sparse. Random graphs have a different shape than the real networks that we're going to look at do. And that's one of the things that we want to talk about in this chapter. We want to talk about different properties of random graphs, and I know there's a lot of math on this slide, and I want to leave it there in case you're so inclined as to want to get into it a little bit further. I did want you to have that opportunity, but the takeaway here is that you can see at the bottom as the network size increases, so we're adding more and more nodes, you have a narrow distribution, and you have increased confidence that the degree of a node is going to be around the average degree. So one of the things that I wanted to point out was this idea that real networks are not Poisson. So what does this mean? What this means for us is that the distribution that a random graph or a random society would follow would have mainly average individuals. So mainly people who have the average degree in the network, and everybody has about the same number of friends. But in the real world, that's not really how it works. We've already talked about that you have most people only have a couple of links. Most people only know a few other people or are connected to a few other people. And then you have maybe one or two people that are hubs, so a very few number of individuals that are connected to a lot of different people. But a random society would not have these hubs. It wouldn't have outliers. And so when we're considering a real network, we can ask ourselves how closely it represents this kind of random society. So how do random networks behave as they gain links? What's the evolution of a random network? Well, the way it happens is, and this is what I want you to see when you're playing around with the Python, is that as you increase p, what you'll find is that you'll start out with a bunch of nodes that are disconnected, and you'll start to gather edges a little bit at a time. And then sort of out of nowhere, you'll have this critical point that's reached when all of a sudden you have a giant component, and it actually resembles a phase transition in physics, something that Barabashi actually talked about in that lecture. And it's pretty interesting. It's just kind of happens very suddenly without warning that all the nodes are now connected to at least one other node in what's referred to as the giant component. So as a random network evolves, you get this giant component that kind of comes out of nowhere rather suddenly as you start to continue to add links. Now, the special thing about the giant component is that, and again, by giant component, I mean a component that's connected. So you have a bunch of nodes that are all connected to each other. So what this is saying here is that the fact that at least one link per node, so if you have a node, you also have a link, the fact that that's necessary to have a giant component, that's not weird, right? Because if you have a connected component, you assume that each node at least has one link attached to it. So each node in the giant component's got to be connected to at least one other node. It is strange, though, that having just one link is sufficient for the emergence of a giant component. So we know that we need to have that, but we don't necessarily expect that if we do have at least one link per node, that's all it actually takes for the emergence of a giant component. And it's also kind of interesting that when this giant cluster happens, it's not gradual. It suddenly happens, and it follows what physicists call a second order phase transition. When this represents the average degree, is equal to 1. And so here's some terminology for describing the network as it goes through this evolution. First, you have a subcritical state where the average degree is less than 1. When the critical point is reached, the average degree is equal to 1. And as the average degree starts to get above 1, then it reaches a supercritical state. And finally, it will be completely connected once the average degree is greater than the natural log of the total number of nodes in the network. And so here's a little bit more information about what each stage looks like. So in the first stage, you have just some what are referred to as trees. You don't have any loops. You have no giant component, just kind of little groups of nodes that are linked together but aren't linked in a big way. When the critical point is reached, we still don't have the giant component, but we could have one. And each of the individual clusters of nodes might have loops at this point. Once you get past the critical point, then you will have this single giant component. So not everybody's connected to everybody else, but you have nodes that are all connected in some way that you could find a path from one node to another in a giant component. And then finally, everybody's connected to the giant component. You have a single giant component. And eventually you could have a completely connected graph. So most real networks are supercritical, meaning that they're in that stage where you have one giant component. So this gives an illustration of, in general, how these particular networks look in terms of connectedness. In the actor network, actually, because of the nature of movies, we have a fully connected graph. It might not be a complete graph, but it's fully connected. So we've established this already, but let's look at how this is true, that real networks are not like random networks. There's 3 things to consider. And again, the math is here if you want to look at it. It's not required. But as this field has grown, people have started comparing real networks, now that we're able to collect lots of data, to the behavior of random networks and finding out that in some ways it's similar, but in some ways it's not. So it turns out that the punchline here is that for both real networks and random networks, on average, the path lengths are small. So on average, we have a small path length in both real and random graphs. And you can see that in the video that's posted from Veritasium as well. Clustering coefficient, though, in real networks, we tend to see that we have high clustering. And this is for a couple of reasons. One, that the rich get richer, the hubs keep attracting more connections, and also because we tend to associate with the same people over and over again, and those people associate with the same people that we associate with. So we have high clustering. But in a random network, we actually have low clustering. This is something that you'll see when you're working in Python and you're doing those calculations. And finally, the degree distribution is not the same in a real network as it is in a random network. So in a real network, we have degree distribution where you have a few hubs and most everybody is connected to maybe a few other people. So most people have relatively small degree and there are a few people that have very large degree. In a random network, most everybody's average. So in a random society, everybody would have about the same number of friends. So again, to recap for this week, we have 3 things to look at in random and real networks at this point. We can consider the path length, so how long it takes for us to get from one person in the network to another. And in both the real and the random case, we have short path length. When we talk about clustering, so how clustered people are, how connected they are, in random networks, we find that we have a low clustering coefficient, and in real networks, we tend to have a higher clustering coefficient. And finally, in a random network, we tend towards the mean when it comes to how many connections we have. Each person in a random network is only connected to about the average degree, whereas in a real network, we have a few people that are very highly connected, and most everybody's not that connected. So to answer the question, are real networks random? Well, no. Simply no. There's no network in nature that we know of that would be described by the random network model. So you might be asking, well, if the model's wrong and irrelevant, why should we study it? Well, like I was trying to say earlier, it's the reference for the rest of the class. So it will help us calculate a lot of different things that we can compare to real networks and understand to what degree it's a particular property of the result of some random process. This will help us understand what's characteristic of the network specifically that we're studying versus some random process that's happening in the network. We can also, if we compare to random networks, see patterns in real networks that are shared by a large number of real networks that all seem to deviate from how a random network would behave. So in order to identify these things, we need to understand what a particular property would look like if it's driven entirely by a random process. So even though it's wrong and irrelevant, it's actually going to be quite useful for us. So these are the things I'd like you to consider when you are working through the applied portion of the class this week. Let me know if you have any questions, and I hope you have a great week.